Hello and welcome everyone. I welcome you warmly to the second week of this course. We'll be talking about the electromagnetic spectrum, the electromagnetic energy. We'll also be talking about how the radiation from the sun interacts with the atmosphere and the surface of the earth. But just before we begin, I want to welcome everyone once again for joining this course. Thank you for taking out time, you know, to be here today. I really appreciate you and your time. If you are new to the channel, I would appreciate it if you subscribe. If you are new to the channel, would appreciate it if you subscribe to the channel. And also, just before we begin for week 2, it would be nice to go over what we discussed for week 1, just a little bit of recap. So the course is Demystifying Remote Sensing. We hope at the end of this course you would have the basic understanding of what remote sensing and concepts are. So once again, if you are yet to subscribe to the channel, we would appreciate it if you subscribe to the channel. So last week we defined what remote sensing was. We established that remote sensing is basically acquiring information about an object without having physical contact with the object, hence the name remote sensing. From we are sensing information about an object or a phenomenon from a remote location. So basically that's what remote sensing is. So we also talked about the forms of remote sensing. We talked about camera remote sensing. We talked about satellite remote sensing, radar remote sensing, and natural remote sensing, where we use our sense organs to sense objects like our eyes for seeing. Our eyes is a sensor. Our ear for hearing. You don't have to like use an ear aid or have your ear so close to something before you like hear what the other part is saying. So those are just forms of remote sensing we discussed last week. Then we moved on to the applications of remote sensing. We talked about all of these applications. So I'll just link the link to the class in the description box, so we can always come back to watch this week 1's video. So we spoke about a lot of application. This is where we are using remote sensing to monitor crop health using NDVI. So we moved on to the remote sensing process. So to explain the process, I'll just go to the last process slide. So for the remote sensing process, remote sensing basically starts from the energy source, which is the sun. So the energy source sends radiation to Earth, which is the target. But before it gets to Earth, which is the target, it interacts with the atmosphere. So the first stage is the energy source. The second stage is the interaction with the atmosphere. The third stage is the interaction with the target. So now, depending on the nature of the target, it's some of the radiation from the sun actually penetrates the target, and some gets sent back. So that's why we have this bitwise. So as it's coming down to the target, it first interacts with the atmosphere, and also after interacting with the atmosphere, once the atmosphere is sending it back, it also interacts. Sorry, after the target is sending it back to the to our sensor, the electromagnetic radiation that has been sent back also interacts with the atmosphere for a second time. We'll be discussing a lot about that in today's lecture. Then it goes to the sensor. Then the sensor captures the data and sends it to a processing center, because they are just the data basically is in like electronic form. We can't really understand. So for us to understand it, it gets sent to this processing center, and from this processing center, it's being processed to something we can relate with, like images. And once we get the data, then we start applying the data for like the applications we spoke about. So that's just a brief recap for last week's class. So we gave an assignment. Thank you for those that are sending in the assignment. I would also link a description to the assignment. I'll also link the assignment in the description box. So the assignments are still open. You can still go ahead and give answers to the assignments. So we'll start today with the we'll start today's lecture in full. That's the electromagnetic spectrum and the interactions with the atmosphere and environment. All right, so just before we move to the electromagnetic spectrum, I feel it's important to actually understand the electromagnetic energy. The electromagnetic energy is a form of energy that is actually reflected or emitted from objects in the form of electrical and magnetic waves that can travel through space. And I think it's important to state that all objects that are above absolute temperature radiate electromagnetic energy. So this is why the electromagnetic energy is so useful to remote sensing. And the sun is the major source of the electromagnetic energy. So we have for remote sensing, we have some sensors that actually captures this energy. Our eyes is also a sensor, but our eyes is not like visible to like our eyes is not visible to all the energy the sun sends, but it's visible to just some very small portion of the spectrum. So the most important source of the electromagnetic energy is the sun. Then we have sensors that actually captures this radiation from the sun. All right, so we'll be moving on. So we'll move on to types of electromagnetic energy. So it actually ranges from the gamma ray to the radio and TV rays waves. So we have the gamma rays, we have the X-ray, we have the ultraviolet, we have the visible light. The visible light is the portion I was trying to explain earlier of the electromagnetic spectrum that our eyes are visible to. So we have the infrared, we have the near infrared and the mid infrared, which are the reflected infrared, and we have like the far infrared, which is also known as the thermal infrared. We also have the microwave, and we have the radio wave. So just to like show everything I've said so far in a way we could like understand it like diagrammatically. Let's move to the next slide. So for all this energy that is actually okay, so we have like different energy levels. Let me just show the image. So we have different energy levels or regions within the electromagnetic spectrum. So these are so we have the electromagnetic energy, right? And now so the energy is actually like is segmented into different regions. So these are like regions we can see, and that's what we like spoke about earlier. The segments which are like the gamma rays down to the radio and TV waves. So this is what we have here as the electromagnetic spectrum. So this energy levels are actually represented, some represented as electron volts, but in this diagram it is represented with the frequency level that is measured in hertz. So some also use wavelengths. So for the wavelengths, the units will be meter, so it could be micrometer or nanometer or centimeter and the likes. So let's just talk a little bit about the electromagnetic spectrum. So the electromagnetic spectrum includes wavelengths of the electromagnetic radiation. So ranging from we have shorter wavelengths, then it goes, and now this shorter wavelengths, so it ranges from shorter wavelengths to like longer wavelengths. And if you notice, It also has like the shorter wavelengths have like higher frequency. Like look at this. Sorry about that. Yeah, the electromagnetic spectrum range from um shorter wavelengths to longer wavelengths. And if you look at the short wavelengths, if you look at the frequency is quite higher. So look at the shorter wavelengths. The frequency is like frequency here is quite higher. Then it goes down. Then the frequency becomes lower. Then the frequency becomes lower. Energy is increasing towards the side of the spectrum, and that's why we have the frequency being higher at this portion of the spectrum. Then it goes down, the frequency becomes lower at this portion of the spectrum. So the microwave and the radio waves, the frequency are quite lower compared to the frequency of the gamma rays, the X-ray, and the ultraviolet. So I just needed to state that the electromagnetic spectrum includes wavelengths of the electromagnetic radiation that are ranging from shorter wavelengths to longer wavelengths. And for the shorter wavelengths, it has higher frequency. The longer wavelengths has lower frequency compared to the shorter wavelengths. So this is the portion of the gamma ray, the X-ray, the ultraviolet, the visible light, infrared, microwave, and radio wave. So we'll just talk about each of this region. We'll just talk about them briefly and how they are useful to our course in remote sensing. So the first parts we'll be talking about is the ultraviolet portion of the electromagnetic spectrum. So we have this is the spectrum, and this is the ultraviolet portion of it. So for the ultraviolet region, the wavelength ranges from 0.3 micrometer to 0.38 micrometer, and the wavelengths have information about the ozone and sulfur dioxide and trace gases in the troposphere and stratosphere. So we'll be moving on to the next region of the spectrum. So we have the visible light, the visible part of the spectrum. So this is the entire electromagnetic spectrum, and right here we have the visible spectrum. So this is just trying to enlarge the visible spectrum first. So the visible spectrum is basically the only part of the electromagnetic spectrum that our eyes can detect. We can't detect any other part of the spectrum. So this is the only part we could see, of the spectrum. So the wavelength ranges from 0.4 micrometer to 0.7 micrometer, and the fact that this portion of the spectrum is the only portion that we could see, so it explains the reason why we can associate things we see with colors, and the primary colors we have are blue, green, and red, which all other colors are actually generated from. So the last point here says that the color of an object is defined by the color of the light it reflects. So to explain this, so imagine when the electromagnetic radiation comes from the sun, and remembering that we can only see the visible part of the spectrum. Now, once that radiation hits any object, be it a tree, be it human, be it the road surface, or anything at all it hits, now that object sends back this radiation to our eyes, and our eyes, being a sensor, captures what is sent back. Now, remembering again that we can only see that visible, you can just see the visible portion of the spectrum. So whatever the object sends back to us, it is what we see, and that's why we can actually differentiate between black or white. We can differentiate between this object or that object, because of what the object is the object is sending back a form of electromagnetic energy in the visible spectrum, in the visible region of the electromagnetic spectrum, and our eyes, which is our sensor, can capture it and say, okay, yes, this is black, this is white. So that explains what we see. So imagine during the day, right? During the day, like there's electromagnetic energy everywhere because of the radiation from the sun. Everywhere is lit, and we can actually see like everything. So as the energy is like bouncing on objects, these objects are like sending back radiations to our sensor, which is our eyes, and then we can interpret this this object. Okay, this is black, this is white. But imagine it is late in the night and you're in a dark room. So there's no source of energy in that room, like the electromagnetic radiation from the sun is not active at that moment. So you can't see. The room is dark. But the objects you could differentiate during the day as black or white, um once you're in the dark, you won't be able to see anything anymore because there's no energy from the sun that is bouncing off those objects and is sending it to our eyes. So like there's no form of electromagnetic radiation at night reflecting on those objects, and the objects like sending it back to our eyes. So there's nothing to send back to our eyes. Then it becomes void of all colors, then it's black. So at night we can't see anything. Imagine it's night and you're in a dark room. So I'm just trying to like take my time to explain this very point here. So that is why we could actually differentiate, or we could actually say the color of an object is black or white because of what it reflects back to us. So I hope we understand that clearly. So we'll be moving on to the infrared portion of the spectrum. So we have the infrared spectrum. So again, this is the electromagnetic spectrum, and this is just trying to bring out the just trying to elaborate what we have here for the infrared portion. So the wavelength ranges approximately from 0.7 micrometer to about 100 micrometer. So it is worth mentioning that it is 100 times as wide as the visible portion of the spectrum we spoke about earlier. Now, the infrared region can be divided into two categories based on their radiation properties. So we have the reflected infrared, and we have the emitted or thermal infrared. So now for the reflected infrared, that's where we have the near infrared that is represented as NIR, and pardon me, there's an error here. This is meant to be IR, no FI. So we have the near infrared, and we also have the mid infrared. So that's what comprises of the reflected portion of the infrared. And now we also have the emitted or the thermal infrared. So that is denoted as the FIR, which is the far infrared. So the radiation in the reflected portion is similar to what we just explained. Like the way it is used in remote sensing is similar to what we just explained about the visible portion of the spectrum. And so for the reflected portion, that's the near infrared and the mid infrared, it ranges from about 0.7 micrometer to about 3 micrometer. Now the thermal infrared is quite different than the visible and the reflected infrared portions, as this energy is essentially the radiation that is emitted from the Earth's surface in form of heat. So that's why it gets the name thermal infrared, because its radiation is emitted from the Earth's surface, and it is in form of heat. So the thermal wavelength ranges from about 3 micrometer to about 100 micrometer. So we'll be moving on to the microwave region portion of the spectrum. So this is just trying to show the the microwave portion of the electromagnetic spectrum. So this is the longest wavelength used in remote sensing. The shortest wavelengths in this range have properties similar to the thermal infrared, because they are actually, so the wavelengths here are shorter compared to what are here. So the point there is trying to explain that the shorter wavelengths right here in the microwave um, in the microwave portion reacts, or sorry, behaves or have similar properties with the thermal portion of the electromagnetic spectrum. That's the far infrared. The main advantage of the spectrum is the ability to penetrate through clouds. So it is actually that property is actually very of interest to us when we are talking about radar remote sensing. It ranges from 1 millimeter to 1 meter. So that's the wavelength portion of the microwave. So next we'll be moving on to interactions with like this spectrum, this electromagnetic energy. The electromagnetic energy, how does it interact with different portion of Earth, like for example the atmosphere and the target itself. So we'll just be talking more about that now. So on the next slide we have interaction with the atmosphere. So remembering this is where the atmosphere is, around somewhere here. So we have the energy source sending radiation down to Earth, but before it gets to Earth, it first of all interacts with the environment, it interacts with the atmosphere. Then from the target sending it back to the sensor, it also interacts with the atmosphere. So we'll be talking about these interactions. Basically, we have two types of interactions we'll be talking about, and that is scattering and absorption. So we have the sunlight, and these are like atmospheric particles, like probably gases and the likes. So when the sunlight comes in contact with the atmosphere scatters that radiation in different directions. So basically, scattering occurs when particles or large gas molecules present in the atmosphere interact with and cause the electromagnetic radiation to be redirected from its original path into like different directions. So the amount of scattering that occurs, it depends on three different items. The first one is the size of these particles. So like how big is the particle. Now the wavelength that is coming, like the incoming wavelength, the wavelength of the radiation, it also depends on that. Like the scattering depends on that as well. And finally, the scattering also depends on the distance the radiation travels through the atmosphere. So like the distance it travels before it hits this particle. So we'll just be talking more about the types of scattering we have. So basically we have three types of scattering. We have the Rayleigh scattering, we have the Mie scattering, and we have the non-selective scattering. So we'll be starting with Rayleigh scattering. So Rayleigh scattering occurs when particles are very small compared to the wavelength of the incoming radiation. So for Rayleigh scattering, Rayleigh scattering occurs when we have particles that are very small. So the particles, imagine this circle is actually smaller compared to the size of this incoming wave. So that's where Rayleigh scattering occurs. So Rayleigh scattering occurs when particles are very small compared to the wavelengths of the incoming radiation. So this could be particles such as small speck of dust or nitrogen and oxygen molecules. Uh, Rayleigh scattering causes shorter wavelengths. Remember, we said the particles are small compared to to the incoming wavelengths from the radiation. So the Rayleigh scattering it causes shorter wavelengths of energy to be scattered more than the longer wavelengths. So now this Rayleigh scattering is the dominant scattering mechanism in the upper atmosphere, and this is the reason we see the sky as blue. So remember we said Rayleigh scattering causes shorter wavelengths of energy to be scattered compared to it causes shorter wavelength of energy to be scattered more compared to longer wavelengths, and it also occurs in the this Rayleigh scattering type of scattering that is dominant in the upper atmosphere. So this is the reason why the sky appears blue during the day, because as the sunlight passes through the atmosphere, we have the shorter wavelength that are visible to our eyes, that is the blue part of the visible spectrum, are actually scattered more in different directions compared to the longer visible spectrum. So during the day, that is why we see the sky appearing as blue, because the shorter wavelengths are scattered more in the atmosphere. I hope we understand that. So that's that about Rayleigh scattering. The next type of scattering we have is the Mie scattering. So Mie scattering occurs when particles are just about the same size as the wavelengths of the radiation. So for example, dust or pollen or smoke and water vapor are like common examples of what causes the Mie scattering. And it tends to affect longer wavelengths than Rayleigh scattering, which affects the shorter wavelengths. So now the final type of scattering we'll be talking about is the non-selective scattering. So this occurs when particles are actually much larger in size compared to the wavelengths of the incoming radiation. So we have water droplets and large dust particles causing this type of scattering. So the non-selective scattering, it actually got its name from the fact that all wavelengths are scattered about equally. So it's not actually selective in compared to like Mie scattering or Rayleigh scattering. So this type of scattering, right, is what causes us to see fog or clouds to appear white, kind of whitish to our eyes. So remember we said this type of scattering occurs when the particles are actually much larger than the incoming radiation. We also mentioned that this type of scattering is what causes fog and cloud to appear white to our eyes. This is basically because we have the blue, the green, and the red lights. They are scattered approximately in equal direction, like they are scattered approximately in equal quantities rather. So like they are scattered in equal quantities. Now that means we have the blue, the green, and the red lights scattered in equal quantities. Now if you combine blue, green, and red, the resultant effect will be white. So that is why we have clouds appearing as white, and we have fog and haze, appearing, giving us that like milkish white color. So that is that about scattering. So we'll be moving on to absorption. So absorption is the other mechanism that is at work when electromagnetic radiation interacts with the atmosphere. In contrast to scattering, this phenomenon actually causes molecules in the atmosphere to absorb energy at various wavelengths. So like it causes molecules in the atmosphere to absorb um the energy that is coming into it. It just like absorb it, like it absorbs all of the energy. So we have the ozone, the carbon dioxide, and water vapor as the three main atmospheric constituents that absorb this radiation. So the ozone serves to absorb the harmful um, ultraviolet radiation from the sun. Without this protective layer in the atmosphere, our skin would burn when it's exposed to the radiation coming from the sun. So our skin will basically burn from sunlight. That's why we hear the ozone is depleting. We should conserve our environment. So basically, um, that is what happens. Like the ozone in the upper atmosphere, it just basically absorbs the ultraviolet light. Now, you may have heard about carbon dioxide being referred to as greenhouse gases. This is because it tends to absorb radiation strongly in the far infrared portion of the spectrum. Um, those are areas that are associated with thermal heat. So it serves as a trap, like it basically trap the heat in the atmosphere. Also, the water vapor in the atmosphere absorb much of the incoming long the long infrared and the shorter microwave radiation. So this is what absorption is all about. So we just have the energy coming from the sun being absorbed basically by three atmospheric constituents. The first is the ozone, which absorb the ultraviolet light. The second is the carbon dioxide, which absorb like the greenhouse gases. And finally, we have the water vapor that absorb the infrared wavelengths. So we'll be moving on to interaction with the targets. So we'll be learning about what happens um, once the incidence energy touches this target. So at point C, what basically happens? So the radiation that is not absorbed or scattered, earlier we spoke about the first point being the sun and the interaction with the environment. So some of this radiation is either absorbed or scattered. So now the radiation coming from the sun that is not actually absorbed or scattered in the atmosphere and reach and interact with the earth's surface. Like, so basically this is what we'll be talking about for the target interaction. So radiation that are not absorbed, basically they're not absorbed or scattered, basically reach the earth's surface and it interacts. The interactions with the earth's surface are in three forms. So the first form is um, absorption. The other form is transmission, and the last form, which is the most important form, is the reflection, because we are basically concerned about energy that is being reflected back to the sensor, and the sensor picks them up. So we won't be like bothering so much about absorption. So basically, absorption is just when this um, when the energy is basically absorbed, like the energy is basically absorbed by the target. So like the target just basically absorbs the energy. And for transmission is when the energy passes through the target. It just like passes through the target. So that is transmission. And we'll be talking much more on reflection, because reflection is when the radiation bounces off the target and is redirected. So this is what the sensor picks up, and we'll be like deliberating more about it. So in remote sensing, we are more interested in measuring the radiation. We are more interested in measuring the radiation reflected from the target. So we have different types of we have two types of reflected radiation. So the first one being specular reflection, and the other one being the diffused reflection. So for specular reflection basically happens on like on smooth surface. So imagine you have a smooth surface. So once the energy, like the incidence radiation touches that smooth surface, all of the energy like is redirected away in one direction. So that is basically what the specular reflection is. Right, the diffuse reflection is when we have like a kind of coarse surface, a rough surface, and energy is actually directed like uniformly in different directions. So basically that's like those are the two type of reflection. So now we'll be moving on to interactions of the electromagnetic radiation with the Earth's surface. So we'll just be taking two samples to talk about, maybe three. So we'll be talking about leaves. How do this electromagnetic energy interact? What happens when the radiation from the sun hits the target? And this time our targets are leaves, like for a tree, for example. All right. So we have a chemical compound in leaves called chlorophyll. And this chlorophyll in leaves, it strongly absorbs radiation in red and blue wavelengths. So we have the this is the energy coming from the sun. We have the blue, we have the green, we have the red, and we have the infrared. So now the leaves basically absorb like energy strongly in this blue and in this red. Like it appears it absorbs energy a lot in that chlorophyll makes this blue region and this red region to be absorbed, and now it reflects this green wavelength. Like it reflects this green wavelength. And remember, we can't see infrared. Like this infrared portion is not visible to our eyes. If the infrared portion was visible to our eyes, maybe the colors of the leaves will be appearing greenish with some other color or something. So but because the leaves, right, the leaves basically absorb this blue and this red, and it reflects this green. So that's why we see leaves as green. For example, when it's all raining, when it's like the raining season, and the chlorophyll content is like very high in and the chlorophyll content is very high in the leaves. So basically the tree becomes very green because it has absorbed all the blue and the red, and it is just reflecting what we have in it's just reflecting the green wavelength. So that's why we like see to our visible eyes, to our eyes, that's why we see green. And when it's when there's like less rain, and the chlorophyll content is actually not so much, like when there's not so much chlorophyll in these leaves, there's less absorption. So like it's basically doesn't absorb a lot of blue and a lot of it doesn't basically absorb a lot of blue. So during this period where the chlorophyll content in that leaf is not actually so high, it reflects more of this red wavelengths. So that's why we see some trees are actually not looking so LD, and their leaves are actually looking reddish, or they're actually looking golden, or they have like this kind of yellow feel. So it's just a combination of this green and red that is being reflected from the leaves. Then I feel it's actually not it's worth mentioning that the internal structure of like an LD leaves of the LD leaf actually act as excellent diffuse reflector of the near infrared portion of the spectrum, because if our eyes were like I mentioned earlier, if our eyes were sensitive to like the near infrared, tree would probably appear to us like that as something that is actually very, very bright, because of the infrared wavelength. So when we want to actually monitor and measure like the health of a crop, you could actually use the near infrared. Um, would actually use the near infrared reflectance. So we can use that inflectance. We can use that reflectance of this near infrared to actually determine if a leaf, or if a tree or a crop is actually healthy. We can just basically use it to determine we can use it to determine vegetation health. So that was part of the application we spoke about in week 1, talking about NDVIs. So the normalized vegetation index. So this is just basically what these are the basics, so to say. So we'll be moving on to the next interaction. So the next interaction we'll be talking about how the radiation interacts with water. So for water, these are the radiation coming from the sun. We have the blue, green, red, and infrared. So basically the water absorb more of the red and the infrared. So you have this, the water basically absorb more of these infrared and red. It's not really sending a lot of this red and infrared back to the sensor, but it's sending a lot of blue. It's sending a lot of blue and a lot of green. Well, not so a lot, but it's sending more of blue and less of green. So it's sending a lot of it's sending a lot of blue back to the sensor, and it's also sending green. So this is why water sometimes appears as bluish green to our eyes, and this is also the reason some water just basically appear like very blue, because once you see water appearing very blue, then it's actually sending back more of this blue, and that is why water is blue to our eyes. So now but depending on the nature of the water body, some water body are shallow, and they are shallow and they are clear. So once this energy like comes in, so far that the water is actually shallow, it touches the like bedrock of the water, and whatever is on the bedrock is what is being reflected back to the sensor, So again, if you have a water body that is shallow, right, and is disturbed, probably it has particles flowing on the surface. So once the electromagnetic energy comes in contact with those particles, like the disturbed particles on the surface of the water, these particles are coupled with the water itself, that absorb the radiation. So what it sends back basically would be blue, green, and also depending on the properties of the particle, they'll be sending that back as well. Sometimes we have trees growing on water surfaces, or we have just leaves on water surfaces. So it will also be sending back those radiation. And also imagine we have the water body that is actually it's very deep, right? Like we have a deep water body, and it is not disturbed. It is just like a flowing water channel, and it's not disturbed, and it is not shallow. It is very deep. So now this type of water bodies actually absorbs all of the energy, like it's because it is deep. So like the electromagnetic energy that is coming into it, it absorbs them, and it will send back. So this is why we actually see, like in our satellite images, we like see water appearing dark, like we see water being void of colors. Like this is what basically explains why we see water as such. And also if you have like a very, very deep water body, but also the surface is disturbed, it basically reflects back it basically reflects the disturbance on the surface of the water. However, we have to have at the back of our mind that it is absorbing the energy, but because of this disturbance, because of the particles on the water surface, it also has to reflect some of these particles, like what you can see basically. So that would be a wrap for week 2. So that will be a wrap for week 2. So we also have an assignment for week 2. So basically there's some things we need to actually, we are trying to demystify remote sensing, and I would like us to also do a little bit of tasks on our own end. So that is basically the purpose of this assignment. So now the first thing is, what do you understand by atmospheric windows? So what I would expect you to do is to just like do a little bit of research and understand what atmospheric windows are. And also I've been using the word reflect. It is actually associated with spectral signature. So because we're actually trying to demystify remote sensing, I really don't want us to use a lot of like professional terms. I want us to use something that even a baby would understand. So I just want you on your own part to do a little bit of research again, and find and get more knowledge about spectral signature. So I also mentioned we'll be talking about interaction with one more. Okay, let's just talk about interaction with one more object, which is soil. I don't have a diagram here, but for the soil basically absorbs a lot of electromagnetic radiation. So when the electromagnetic radiation comes in contact with soil surfaces, depending on the depending on the moisture content of the soil, it basically either absorbs almost all of it and sends a little back. So that's why I actually gave this assignment. So we would, if you like do a little bit on, if you like do due diligence on this assignment, you'll be like seeing different, you'll understand more on this interaction of the spectrum or of the electromagnetic energy with different earth surface. So we have it's interact differently with the way it interacts differs from target to target. So say we have leaves, say we have water, say we have soil, and the likes. So I just want us to do this assignment. So next week is week 3, where we'll be talking about types of remote sensing. So I'll be expecting you in the next class. So thank you so much for tuning in and joining us in this session. We appreciate every bit of your time. So if you have questions for us, you could actually leave your questions on our Slack channel. So we also have a Slack channel where we get to talk about our upcoming events. So we invite everyone around the world to join us. So we would also drop a link in the description to the Slack channel. So if you've not subscribed to our channel, we'd also appreciate the whole lot. You'll be supporting us just by giving us a like, a thumbs up, and subscribing to our channel. You could also turn up post notification to get notified whenever we upload new content. So once again, we thank you so much for your time, and we hope we've been able to demystify remote sensing, at least to a point whereby you understand what we've been saying so far in week 1 and week 2. So that'll be a wrap for this class. Thank you again, and bye.